Okay, welcome to this video. We are in our notes, our Unit 7 notes. We've done all this. So for our next task, we're going to be moving on to circular motion. Now you took these notes on the last video, and make sure you did, because if you didn't, go ahead and fill in those bullets. They were given in the prior video on circular motion. And we solved this problem, and now here we are on page 10. We are going to fill in these notes on page 10, and then your homework is going to be to solve numbers 3 through 9. So you're going to do 3 through 9. That's the homework. Perhaps I'll add a couple more, but for right now it's 3 through 9. Just check the email. Okay, on this page 10, we are going to be analyzing objects that move in circles, and we'll analyze the forces acting upon those objects. The big rule that we have to remember, and you don't need to write this down, but the big rule is forces pointing into the circle toward the center, we make positive, and forces pointing out away from the circle, away from the center, we make those negative. So here's our first example, and this is the top left box in your notes. It's the case of a pendulum moving in a horizontal circle. The pendulum, we can draw this picture, is at some angle, and it's moving around like that. We know gravity pulls it down, and the other force is tension pulling up along the string. The string has been stretched slightly, so this end is getting pulled back in toward the middle, just like when you stretch a rubber band. Let's put those forces here again. Tension is at an angle, so we can draw the components. There's the Tx and the Ty, but the object is moving around a circle that's in the horizontal plane. So the vertical forces all have to cancel out. These two forces are equal. Ty is equal to mg. So what forces do we have left? Well, this force isn't still there because we broke it into the components. So the only force left, the net force, is Tx. But if we take the tangent of this angle theta, it's opposite over adjacent, so Tx over mg, we see the net force is equal to mg tan theta, and I got that by cross-multiplying right here and substituting in for Tx. Next up is a planet moving around a star or the sun. So here's the object in the middle, and here's the object which is in orbit. There's some velocity this way, so the object is orbiting clockwise, and the force that pulls the object toward the center, the force that turns the mass, little m, is gravity. There's no other forces, so the net force is just Fg. But we know that Fg is equal to big G times the product of the masses divided by the square of their separation distance. So r is the distance from the center of big M to the center of little m. And I'm going to draw it over here so that my diagram doesn't get too complicated. But sometimes a problem will not give you r, little r. Instead, it will give you the radius of the thing in the middle and the altitude at which this guy is orbiting. So pretend for a moment that the center object is the Earth, and this is the moon or a satellite. If this is what they give, you have the same force as the net force, it's gravity, and the same numerator, but the denominator now is the sum of little r and the altitude a. Next up for us is a car moving around a flat circular track. Here's the track, here's the car, and it's moving this way, let's say, anti-clockwise or counterclockwise. Now, what's the force that pulls it in toward the center? It's static friction. Let's look at this again from the side. Here's the road, and we're going to view the car like we're standing right here, looking at it head-on. So here's the car. We see gravity. There's also the normal force balancing gravity. We'll use N this year for normal force. And then pulling the car in toward the middle is static friction. Because what's the car want to do? It wants to fly off the side of the road, right? This way. And so instead of flying off this way, the grip, the static friction, keeps it in place, pulling back the other way. So these two forces cancel. N is equal to mg. And that means the net force, what remains, is just static friction. There's a final equation we can list, which is the equation for static friction. Mu times N, the normal force, where mu is the coefficient of static friction, or Mu is the roughness of the surfaces. Now, this is the equation for the maximum static friction force. Static friction can equal this value or anything less. But what if instead of having our car like that on a horizontal track, we have a banked circular track, or a track at an angle? Well, gravity still pulls down, but the normal force is always perpendicular to the surface. And static friction is always parallel to the surface. So we could draw the x and y components of gravity, and instead of calling this the y component, we'll call it the component perpendicular to the surface. Because here's the surface, here's the component, and they make a right angle. This component is perpendicular. And this component down here is the parallel component of gravity, parallel to the surface. Well, these forces cancel. Gravity's not there anymore because we broke it into components. So the net force is just, there's two that don't cancel out. There's static friction that doesn't cancel, and Fg parallel. That's the only thing you need to know for these problems. We will not solve any actual quantitative problems with this scenario. Next up, a roller coaster ride. So here's the roller coaster ride, and there's the roller coaster, and it's going to swing all the way down to the lowest point. Now, you may not think this looks like the cart is moving in a circle. After all, there's this big flat part right here that's not curved at all. But at the top, we could imagine this circle that the cart is moving around just momentarily. And at the bottom, the cart momentarily moves around this circle. So there has to be a force pulling it toward the center, and in this case, the force is pointing up, pulling it toward the center of the circular path. Okay, so what are those forces? Well, there's gravity in both cases. Gravity always acts. And now we know there's also the normal force from the track. But the normal force is smaller than gravity in this case, because now the normal force doesn't cancel all of gravity, it only cancels out part of gravity, and what remains is the net centripetal force. You need some unbalanced force pulling down toward the center of the circle. So because mg is into the circle, it's positive. The normal force is out from the circle, so it's negative. But over here now, look at this, mg is out from the circle, so it'll be a negative force. So how can I draw the normal force? Is it equal to mg? Is it smaller? Is it bigger? Well, it has to be bigger, because the unbalance, when you add these two up, there must be some unbalanced amount pointing toward the center, pointing up. So the normal force must be larger. Normal force is positive when we add up the forces to get the net. N is positive because it points into the circle. Mg is negative because it points out from the circle. The final scenario is a pendulum swinging around in a vertical circle. And we've got our pendulum going clockwise in this case. And then we'll also look at the pendulum at the top of the circle. Okay, so what's the net force? Well, we've got gravity in both cases. And then this string is taut. The two edges have been stretched slightly, so there's tension pulling back. We're going to see there's a tension force pulling down here as well. But now the gravity force has to be smaller than tension. We know gravity has to be smaller, this outward negative force pointing out from the circle, because there has to be some unbalanced amount pointing up into the circle. So T has to be a little bit bigger. That's why my tension arrow is bigger than mg. Over here, we've got a similar scenario, except, well, wait a second. The string has been stretched out, so this end is pulled back down toward the middle. The ends of the string are pulled back toward the center of the string. And so now both forces are positive. They both point into the circle. And the net force is this. Here's the thing about this scenario. What if we consider the moment when it's at the side, the ball? Well, we've got gravity pulling down, and the tension would pull this way along the string. So is this object, does it have a net force pointing toward the center? Not exactly. And that's why this is not a perfect case of circular motion. The circular motion is not uniform because at the sides, the net force isn't directed toward the middle. It's at some angle. When you add these vectors together, the net will be at some angle after the tip-to-tail addition. Moreover, at this moment, we're speeding up. because the mg force is in the same direction as velocity. You're going down this way, and you're getting pushed in the same direction, which speeds you up. The t force is responsible for turning the ball at this point. Mg is speeding the ball up at this point. So it's not possible to go around at a constant speed in this simple scenario where you've got a string connected to a ball.